Are you not saving it? You're not saving it?
Olivia, you have a couple of assignments that we're missing too.
Oh yeah,
Okay.
Can you get me the assignment?
No, they're over there waiting for you. You can do it. You're fully capable.
Intelligent disabled. So you need to.
Where's my pass? Olivia.
That's Mr. Townsend.
No, that's Olivia. It's got a name tag. that
I don't
says
have
Olivia.
this hairstyle. I don't have this hairstyle.
Okay, I'll fix it.
You fix your hairstyle?
Around at 92.
Okay, so I should
No.
do one of them then.
Oh my gosh, this is so ugly.
Well, you have to do good on both. So I got a 5 out of 5 on both.
No, I don't have that
I have 5 out of 5.
hairstyle.
Then as long as you get
That's you.
5 out of 5 on this one. Yeah, I'm out. Got my
Alright, there we
You
go.
have black hair.
Well, it's Gov and we took the exam on Tuesday, so.
Are these
Right.
right?
Locked in the AP exam,
I
right?
don't know if I'm missing a page. Is that one's?
There should be 2 and then.
There's none?
Yep, that's it. There's 3 of them.
Mr. Townsend. I have a 0 in the grade for 120.
Oh, okay. Just put it back in and I'll be able to fix it.
No, I never do
What?
Miss Penner's not here. May I stay in this class? Fine, because I won't be disruptive. Promise.
Yeah, I just got a couple.
She marked me absent. Oh my. Not absent, present. You allow her to stay and don't allow.
I didn't
allow
say she could. No. You need to go wherever you're taking attendance.
She already took my attendance.
Okay, well,
No one's in there. No one's in that class right now.
what do you mean no one?
In Miss Penner's class. Because we already took our exam on Tuesday.
Surely somebody needs to show up.
The chairs are like, none of them are stacked.
You can go to the reef room.
And you were the person who said, I have chemistry. I have chemistry too, but like.
Reef is a good person and he will allow you to stay.
I got kicked out last time.
Reef?
I walked in and he said, go away.
Oh my god.
He does not like me.
He likes you. But Mr. Townsend doesn't like me, right? You hate me? Because I draw ugly things about you. Look at my drawing. Okay.
Do you have a verdict, Mr. Townsend? Oh, also I need to take a quiz.
Okay, you can take the quiz, and then I'll go check on this stuff. But you have to wait for me to get to restart.
That's a microphone? Hello?
All them are missing. The coach is like, well, you scram. One of the coaches is like, well, you could go to graduation, drive down. Then you won't do, like, he was like, I haven't been here. No, he was like, Bill, I need to go get that. I'm 23.
I'm grabbing my homework.
All right, good morning, guys. The bell should have gone off if the bells were turned on. I need your assignment 123 from yesterday, and then clear your desk off for the quiz, please.
Yeah, but like, I also gotta take it. I can't see. Yeah. Why don't you trust me? Johnny said he was gonna do that. He could just like, Are you guys ready for this?
were both going yesterday, weren't you?
This is the Beatles.
Yeah. I'm not.
See, why don't you take it, but I
Where's the stapler?
Tell me.
The one that's. right
I
in
just
front
saw
of
the
you.
stapler.
I already turned in my from yesterday, but I'm not going to so I just put it back.
Okay, I'm following you. All right, these are the last 5 major points. So double check as best you can before you turn them in.
Sarah, can you get me
This one sound good for the main quiz. Whatever the hell. Just Louis.
Will I get extra points for doing this?
No.
No? Okay.
Points for this though.
Thank you.
Wait. What number was that?
93 A and B. I did both of them.
93A?
And B. I
A?
did both of them.
Oh, okay. I didn't even notice that.
Thank you.
Okay, we still got a few more quizzes out, so try to give them another minute or two, please. Okay, if you are still finishing, please try to finish up in the next minute or two here. Come turn that in. So of course this is our last day, so I've got 2 more practice FRQs for you. So the ones you did yesterday were all different types, 1 particle motions, 1 graph analysis, 1 rate in, rate out. So if you feel good about all 3 of those, you were happy with your score, then you probably can check that off of your study list for your AP exam. But if you are still struggling with 1 or more types of those, I still think that's the most important thing that you can do. Those FRQ types are all but guaranteed. FRQs are just worth more than multiple choice. And typically students don't worry about multiple choice too much. So anyway, that should be your final indicator of if you need to practice more of those or not. Plenty of them on the class website under the FRQ database. So if you don't remember where that is, then I can show you. So today I've got you 2 last FRQs, and today these are both table FRQs. So I have not emphasized the table FRQs as much as the others, not because they won't be on your AP exam. In fact, I can all but guarantee one of your FRQs will be based on a table, but the table FRQs, the questions they ask about those tend to vary quite a bit. So I feel like you have to practice a lot more of those to make sure that you're in good shape for that FRQ type. So it's not that it's not important, it's just that it's not as important as being ready for particle motion, rate in, rate out, and graph analysis, in my opinion. Any questions about any of that stuff? Okay, I would like, I did switch out my daily meme since y'all were so upset yesterday you weren't going to see Mr. Tarbutton's daily meme, so this is his that he sent me. I would like your 2 table FRQs today, if at all possible. If you just happen to run out of class time doing that, I guess you can finish them and email me a picture of them, but I do need them / want them before Monday in the AP exam. I do not want you doing these after the AP exam only because you're trying to bump your grade up. If you're trying to bump your grade up, get more grades in, you need to do it before the AP exam, not after. So if you had some missing work, if you haven't been turning anything in recently, which I don't think is anybody in here, but again, if you can't get it to me in class today, make sure you email it to me sometime this weekend. I don't care if you send me 20 emails and each email is a different assignment, that's fine. If you had 20 things that were missing from recent stuff that you never turned in or you finished up, that's fine. You can send me 20 emails and I would not be upset about that. If you want to send me 1 email that has 20 attachments for 20 of those grades, that's fine also. But I do want it before the AP exam. Okay, the other thing I have for you today, before I give you the rest of the time to study and to finish these 2 table FRQs, is I have a class video that I like to show. And I always save this for the last day we have together because I've kind of fibbed to you guys a little bit. You really don't need a full year of calculus to learn calculus because this guy explains all of calculus in under 20 minutes. So, it's pretty silly. You don't have to fill anything out. All I do is ask that you watch it. And of course, if somebody's trying to summarize calculus in under 20 minutes, they're just hitting the most important highlights. So, if he says something that doesn't sound familiar, you don't remember, those would be good things to ask about. But otherwise, other than the speed that he goes at, you should be able to follow and understand and piece together all the stuff that he's talking about. So again, all I'm asking you to do is to watch it and to try to pick up on all of the math since it's only highlights.
Alright, so now we're going to try and do the impossible. We're going to try to do all the calculus in under 20 minutes. So we have to really fast go through the whole course. Let's begin. The first two basic...
Oh, you should take notes too, because your final exam is going to be a video of you doing this in 20 minutes also. So.
Basic issues of calculus. Two big questions. What are they? How do you find instantaneous rate of change? How do you find how things are changing instantly? And then, completely separate from that, how do you find areas under curves? Two completely different questions. Turns out answers are completely related. Let's see how they go. Question one. Instantaneous rate of change. What are we going to do? Well, what you do there is you first remember what does rate mean? Well, rate is just change in distance over change in time. It's easy as that. Distance equals rate times time. Not a big deal. Okay, now what do you do with that? Well, if you graph a function that represents sort of distance against time, then what do you notice? If you want to look at the change in time and the change in distance, what do you got? You actually got a slope of a line. Right? This is slope, rise over run. Change in distance over change in time. Distance over time. So you got a slope. So automatically we see a really neat thing. We see that the average rate of change between 2 points is equal to the slope of the line connecting them. Well, that's really cool. By the way, what about lines? Maybe you forgot about lines. Remember about lines? Okay, no problem. We can do lines. We can do lines. Lines. Y minus y1 equals m times x minus x1. This is the point slope form. All you need to give me is a point on the line, x1, y1, and a slope, m. You give me those two pieces of information, I can always write down the line quickly. Always. Never forget it. Okay, fine. So now we're back to here. Now we can find average rate, and what do we see? Well, in fact, a line that touches the curve at 2 points is sometimes called a secant line. So in fact, we just discovered that the average rate, change in distance over change in time, is equal to the slope of the secant line. Cool. So all you have to do, you want to find average rate, connect the 2 points to the line, find the slope, you got the average rate. No biggie. But that's not what we want. We want instantaneous rate. So how do you do that? Well, what would that be? Well, if I want to find instantaneous rate here, what would I do? I'd make that secant line closer and closer, bring these points together, what I'm converging to? I'm coming to a tangent line. Wow! Instantaneous rate of change equals the slope of the tangent line. So we want the slope of the tangent line. Well, what's the slope of the tangent line? It's change in y over change in x, change in distance over change in time. But now the change in time from that point to itself is 0. 0 over 0. So I'm getting 0 over 0, which is complete garbage, and that is a big problem. Our first major problem of the course. Okay, so what do we do? Well, we can that. Distance equals rate times time. We're going to can that. Instantaneous rate of change, I really want that. So what do we do? Well, how do we get that 0 over 0 problem to go away? The answer is we inch up to it. We just approach the 0 point. And what would that look like? Well, let me remind you what you've done when you were a little teeny kid. When you were a little teeny kid, this is what you're looking at. You're looking at a value of function at a point. Value of function at a point. Okay, not a big deal. There it is. F of A, it's that point. But you don't know anything else about the function. You don't know what's going on around there, because all you're looking at is F of A. You open it up. Woohoo! Function will be quite interesting. Who knows? Okay, but now what I invite us to do, and what calculus invites us to do, is to look at the function this way. Cover up that point and look at everything else. Open the window, look outside. That's where calculus is. And what you see here is we can see what things are approaching, and we can actually determine the idea of a limit. The limit is what things are approaching. We don't care about what actually happens at that point, only what things are approaching. Armed with the idea of a limit, what can we do? Well, now we can return to the question and figure out, let's take the limit as delta t goes to 0. What do we get? We get 0 over 0. That is called an indeterminate form when you get 0 over 0. So what do? You've got to do some algebraic gymnastics. You've got to factor the top and cancel with the bottom. You can try to multiply by the conjugate. You can try to combine the fractions. There's all these tricks in the trade to actually reduce it to something that you can actually find. So you find the limit. Okay, but once you find the limit and you take the limit as delta t goes to 0, what do you get? You get the answer to the question, how do you find instantaneous rate of change? The answer is what we call the derivative. And what's the derivative? It's the limit as delta x goes to 0 of x plus delta x minus f of x over delta x. Looks pretty confusing, doesn't it? It's just rate. It's distance over time, but now I'm letting the time go to 0. Not a big deal. So that's the derivative. Bingo. We're done with the first question. And so now what do we see? Well, we see now, we come back here, and the derivative, in fact, gives us the slope of the tangent line. Well, that's really cool. You want to find the slope of the tangent line ever like, you just take the derivative, and that gives you the slope of the tangent once you evaluate at the point you want. Great, but for free, we answer first question. Because remember, the derivative also represents the instantaneous rate of change. So you want to find out how things are changing? No big deal. You take a derivative, plug in, and that will tell you how things are changing at that instant. Okay, great. So now we know all about how to graph these things, how to look at these things, the derivative exchange velocity, boom, we got all underway. Now let's take a look at some applications. What can we do with this? Well, how would you take derivatives of complicated functions? Well, if you got a product, use the product rule. Remember the product rule? Don't memorize the formula, memorize the chant. First times the derivative of the second, plus the second times the derivative of the first. So the derivative of a product is this. It's not the product of derivatives. You got to use the product rule. We got 5 minutes to figure out, folks. I got to move faster. What if you have a quotient? Well, then use the quotient rule. And what's the quotient rule say? You got a quotient. You take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. That's the quotient rule. That's what you use when you have a derivative of a quotient. Okay, great, no problem. Now, what if I have a really complicated function? What if you have a function like this? It's got insides. It's got guts right in there. So you've got something like this. And you want to take the derivative of that. What do you do? Well, you got to use the chain rule, folks. This is a thing that you can chain together. There's an inside, there's a block right here, there's a whole big block there. And then you've got an outside. Take the derivative of the outside. So the derivative of sine of block is actually cosine of block. So it's cosine of block, and what's the block? The block is going to be 3x cubed plus 1, and then you multiply that by the derivative of the inside. The derivative of that turns out to be just, let's see, 9x squared plus 0. And so there's the derivative using the chain rule. The idea is to peel off like an onion. Just peel off, keep peeling off the outside until you get to the inside. Always remember though, when you take the derivative, it's if you have sine of block, the derivative is cosine of the block. Don't put the derivative there, put the block and multiply by the derivative of the inside. That's the key to the chain rule. Now we have the chain rule. Okay, so what about when you have functions that aren't functions? Like what if you have things that are relations? Like x squared plus y squared equals 1, like a circle. How do you differentiate that? How do you find dy dx there? Well, the answer is we use something called implicit differentiation. Implicit differentiation, how does that work? Well, you've got to remember that dy dx, that's an object, that's a noun. And d dx is a verb, it's a commandment. Take the derivative with respect to x. So you differentiate this with respect to x, and what do you see? Well, you see something just like this. What you do is, you say, okay, I'll take d dx of x squared plus y squared equals 1. The derivative of x squared with respect to x is just 2x, not a big deal. The derivative of y squared, remember how I think about this? I think about this as clumping all this together. And I see this as a block squared, so I actually use a chain rule, which we just developed. And the chain rule says the derivative of block squared is 2 block, and then I multiply that by the derivative of block, which is the derivative of y with respect to x. That's called dy dx, folks. The derivative of 1 is 0. And now you can actually solve this for dy dx by bringing this to the other side. That'd be a minus 2x. You divide by the 2y, and you see dy dx equals minus x over y. And there's the answer. That's implicit differentiation. Just go right through and differentiate implicitly. When you have a relationship, you can still find the derivative. Great. We're making progress here, folks. We are cutting through this stuff. Well, now that you have derivatives, what can you do with that? Well, if you think about it as velocity, you get instantaneous velocity. If you take the derivative of velocity, you actually get the change in velocity, which is acceleration. So we get acceleration now, we get velocity. Acceleration is just the second derivative of the position. So we can actually take derivatives upon derivatives upon derivatives as many derivatives as you want. So it's great. We can do that. So higher order derivative, no problem. What can you use these things for? Okay, we know it's true for velocity. We can use it for velocity. What else can you use it for? Well, it turns out you can use it for linear approximation. Suppose you've got some wacko function. You got some wacko function like this, woo, and you actually want to figure out the value right here, and you don't know what that value is. But you know nearby there's a point that you can actually compute. So what do? You find the tangent line approximation because you remember the tangent line closely emulates the activity of the function. Tangent line closely emulates the activity of what the function is doing. So it looks the same there. So you find the equation of the tangent line, and then plug in the mysterious point, then you're all set, because you can approximate the value by plugging into the tangent line. So how would that look? Well, that's called linear approximation. Here's the formula. Don't bother memorizing it, just think about it. What you got to do is you got to find the equation of the line that's tangent at the known point, which is x here in this case, and this is going to be x plus delta x. The known point plus a little t offset, so you approximately equal to the derivative times the change in x times the function. I mean, plus the function. So that's it. That's the whole thing right there. Linear approximation allows you to compute things. Computers actually work this way. Computers know calculus. Everyone knows calculus. You've got to know calculus. Okay, now, what else can you do? Well, suppose that a derivative were to be 0. Well, how could that possibly happen? That could possibly happen because maybe the function goes like this, and I see the tangent over here has slope 0. Or maybe the function goes like this, and I see the tangent has slope 0. In particular, if the tangent equals 0, maybe we have a maximum min. Also, maybe the slope or the tangent doesn't exist. Like if you have a wave kind of thing, a cusp, very pretty cusp like the waves. Well, that might be a max, that might be a min. So in particular, you can find out when objects are maximized or minimized. You can find the maxima or the minima very easily by using calculus. What do? You take a derivative and you see where it equals 0 or where the derivative doesn't exist but the function does. Those give you candidates for possible max and min. And what can you use that for? Well, you can do all sorts of max and min problems. You want to maximize profits, you want to minimize costs. Oh my God! 20 minutes? No. It's only 10 minutes left. I'm trying to figure here, folks. I'm not going to go up for it. 10 minutes left. Okay. So you want to maximize cost, you want to minimize cost, you want to maximize profit, you want to maximize area, you want to minimize volume, whatever it is, set up the problem really carefully, figure out exactly what you want to optimize, take the derivative, set it equal to 0, solve, find out where the derivative is undefined, and you've got it made. Really not a big deal. However, you should always remember and never forget the fundamental method of solving problems. So remember how you solve all of life's problems. The first thing you have to do is understand what you're being asked. You can't answer a question that you don't understand. The next thing you do after you understand what you're supposed to find, what you're being asked is figure out what you know. List every single thing that you know, every single fact. Maybe it's superfluous, maybe you don't use it, who cares? Write it down, understand it, make it your own. And then the last thing is, take the information that you know and see a relationship between that and the thing that you see. Try to find a connection. Once you got the connection, then you're on the road to actually find a solution. That is a simple method for finding any single answer to any single problem. Another application, if you think about derivative as a rate, is looking at related rates. Suppose, for example, that you actually have a ladder, for example, that's falling down. The ladder is falling, and you don't want to be sued, but the only thing you do know is how fast the bottom is falling, you want to know how fast the top is falling. What you need to do there is, if you know this rate, you can find that rate by linking them up with a connection. In this case, the connection would be the Pythagorean theorem. You can take the derivative with respect to time, because here you see the variable, the thing that's independent that's always changing is time. Time keeps on ticking into the future. So you keep going like this, you actually solve this, take the derivative using implicit differentiation, differentiate with respect to time, and plug in what you know how this is changing, and that tells you how this is changing. Pretty cool. That's called implicit. That's called related rates. Suppose, for example, you drop a stone into a very, very still pool. You have a ripple effect that makes concentric circles that are getting larger. If you know how fast the radius is changing, you can find how fast the area is changing because you have a connection between area and rate. Area equals pi r squared. So there you go, related rates. If you know how one rate is changing, you can find out how related rate is changing. Okay, what else do you use derivative for? Well, the other thing you do is actually graph really accurate pictures of functions. Finally, you can figure out that a parabola looks really pretty and bowl-like, like this. And it's not something really exotic, but it's just a nice pretty bowl. How do you do it? Well, you just start taking derivatives and analyzing things. First, you find the critical points. Those are points where the derivative either equals 0 or the derivative is undefined, but the function is defined. So for example, in these examples right here, you'll notice that the derivative equals 0 here, the tangent is horizontal right there, the tangent is horizontal here. In this example, the tangent is horizontal here. And then where does the derivative not exist? The derivative doesn't exist here. The derivative doesn't exist there. Those are candidates for maximum. Those are called critical points. Then what do you do with those things? Well, you set them up on a number line, the x-axis, and you look at the intervals all around it, and you see whether the derivative is positive or negative. If the derivative is positive, that means slopes are positive, so the function must be increasing. If the derivative is negative, then that means the function must be decreasing. So you can see that the function, for example, here is decreasing, then increasing. Here you can see it's increasing, then decreasing, then increasing. So you can see where it's going up and where it's going down by the sign of the first derivative. That also determines whether you have maxes or mins anywhere. And that's called the first derivative test. Now, how do you figure out the curvature? The curvature is given by the rate of change of the derivative, how the derivative is changing. So what you do there is you take the derivative of the derivative. So you look at the second derivative. And where the second derivative is 0 are potential points of inflection, points where the concavity changes. This is concave up, it's curving upward. This is concave down, this is concave up. So the cup is sitting up, the cup is sitting down, concave down. So here you see the second derivative is positive, then the second derivative is negative, changes here. Now it's sitting up, it's positive, we're concave up. Here we're concave up, second derivative is positive. Now here we see it's concave down, second derivative is negative, and second derivative here is also negative. This is a cusp point, the derivative doesn't exist there. This is a point of inflection, this is a point of inflection, this is a point of inflection, and that's a minimum. So just by taking derivative and then second derivatives, you can actually figure out and graph a very accurate sketch of even very complicated, almost scary looking functions. By the way, if you have fractional exponents, expect cusps. That's my warning for the day. Okay, now, if you got really exotic functions that have denominators, then actually you may have asymptotes. So don't forget that a vertical asymptote is where the function, after you simplify it, the bottom equals 0. So wherever the bottom equals 0, after you simplify and reduce, those are going to give you your vertical asymptotes. Horizontal asymptotes, you take the limit as x goes off to infinity, as you go off to the horizon, and you see what y value you're trying to land to. If you're landing somewhere, then you know you've got a horizontal asymptote, and y equals that value. So you can put the asymptotes, and then you do all the calculus, get the curvature, see exactly what your view of picture looks like. And that was the end of differential calculus. Great, no problem. Now what? Well, now we move on and look at the exact same thing we just did backwards. So we look at math chapter. Oh my goodness, I have only 5 minutes left. So math chapter, here we go. So the idea is, if I tell you what the derivative is, how can you find the function whose derivative is that? Well, it's the notion of an antiderivative. So how do you actually find antiderivatives? Well, we said one was that, if you want to find the antiderivative of x to the n, it would be x to the n plus 1 divided by n plus 1. Take the derivative of that, so you get x to the n. Unless n equals -1, then you're looking at the integral of 1 over x. And what's the integral of 1 over x? Well, it's the natural log of the absolute value of x, because the derivative of natural log we already saw was 1 over x. So great. Now, how can you find exotic integrals? Well, remember that d dx represents differentiating with respect to x, and so therefore the integral with respect to x represents to integrate with respect to x. Now, if you have a very complicated thing there, with an inside and outside, you might be able to untangle that, which potentially was made by the chain rule, by using substitution. Let u equal some big block, and the big block's derivative should appear somewhere else in your integral. If you got that, it sounds like a good candidate for u to use substitution, and then you've got to change the dx to du by taking derivatives and seeing what du equals in terms of dx. So that's the u to substitution. You got that going on here. And now what do? You can take that and look at studies of motion again. Now I can give you acceleration. If you integrate, you get velocity. If you integrate again, you get position. So vertical motion, not a big deal. Lands, no problem. Things moving in space, like this thing here. Watch it, folks. You can get that. Anything that moves, anything that moves, we can now analyze whether you have crabs or whether you have a bike. It's not a problem anymore, folks. If it's movement, we can differentiate and figure out what it is. Not a problem. Now, where does this lead us? Well, it brings us back to the very first question of the course, which was how do you find areas under curves? We have to answer that. We haven't done yet. It turns out the surprising answer is that it's the fundamental theorem of calculus. And the idea is if you want to find the area under this curve from A to B, right here, if you want to find that area, then how do you do it? It turns out that if that function is called, let's say, f of x, then all you do is integrate from A to B f of x dx. Because you're summing up little rectangles in here that are base, small change in x, base times height, which is the function you go from A to B, and this equals f of capital F of B minus capital F of A, where what's capital F? That's the antiderivative. So if you take the derivative of capital F, you actually get little f of x. So just find the antiderivative, plug in the big point, plug in the small point, subtract, that will always give you the area under the curve. You can look at areas with more exotic things. For example, if the thing actually goes like this, then actually, this is actually not very x easy. The rectangles aren't very clear. The rectangles change from going from green to green, over to green to orange, and to orange to orange. It's not very uniform. However, if you put the rectangles in this way, and stack them this way, now you're summing with respect to y. And so here you would actually sum this with respect to y, so you would integrate this dy, and put the rectangles in this way, and you put the rectangles in that way, and stack from low to high, and you stack the rectangles like this. Okay, that is all of calculus. I did it in under 20 minutes. That's what it is. Go back, think about it, have fun with it. Congratulations, folks. You just finished calculus 1. Have a good time, celebrate, good luck in the final. Bye.
So, you think you did a good job?
Yeah. Fast.
Okay, so again, nothing specific you need to get out of that. Just
Hopefully all that sounds familiar to you since it was all open enough to make a 18-minute video. But squared, you take that out.
I'm sorry, I'm putting the agenda back up.
Alright, so unless you have missed recently, you should have just these 2 table FRQs left to go. And you've got about 58 minutes to do so. So should be plenty of time.
Took the quiz from Tuesday. Thank you.
If you need a makeup quiz or something, though, you'll have to tell me.
Mr. Townsend, I need to do all the quizzes for this week.
All of them? Do you want them all at once, or do you want? How's your AP test been going?
I did a lot better than I thought I felt like I did. I think I was really unprepared, but I promise I just like studied for well, I'm really sorry a lot. Well, but I also have like not the best school teacher, no one can school. No
Afterwards in 20 minutes video.
I did. Saw you pulled it up.
I was saying like my 1 point suggestion.
Oh, you did.
Were you here yesterday?
Yesterday?
You did mention your test authorities. I just completely forgot that. That's why your pictures of that doesn't work. Lost point. Equal points. You took a picture of the screen yesterday also. I did? Oh, that was me zooming in. I can't see.
She's supposed to wear glasses.
Why didn't you tell me you said you were fat? No, I was in it. Well, I know for next year now. No.
Plus, the BC classes are usually smaller, so you'll be like the only person up front.
Oh, that's like Kelvin.
Put me in the back.
Situation.
Put me in the back, please.
No, you can't see.
I just listened to you.
That's not good enough.
Hey, does anyone know how to make space on your drive? Does anyone know how to make space on your drive? Or your disk?
Oh, Joe knows how.
No, I don't.
Never mind.
I
He has to
think I
figure that
got
out.
one thing with that problem, my Chromebook had that problem, and then it just ran into it.
Probably just gotta delete a bunch of stuff.
I've tried that.
I've been trying that.
Yeah. You might have to take it to the, sometimes my Chromebook wouldn't let me sign in. Install it.
So you take your pencil lead and put it like in the USB.
I took it to the
Should
section,
use someone else's phone.
fixed that problem. When they fixed that problem, my disk space was down.
Dude, I would actually do it.
There was they sent, some administrators sent an email to all the teachers.
No. Just wait till I send it, I will let you change it.
Yeah, you better do it.
I'm cheater.
Yeah. Yeah, please don't. Actually, you can. This thing's like 6 years old. My car was actually at my house. No, I need to read. I have it. About a year.
Low key, seriously, I could destroy my